Alright guys, so I thought I'd do a video for you on radicals, and so these are some problems from Alex, and I thought I'd do them for you. You can kind of watch the video and get a feel for it, and it may help you with some of your work on Alex. So this is on radicals up here, and you can ask the question, what is a radical? So radicals, probably the most famous radical is this, which means the square root. So if you put like a 4 in there, it means that's equal to 2. Because 2 is a number you square to get back 4, or if you put 9 in there, so the square root of 9 is equal to 3. Besides square roots, you could have cube roots, and so we write it like this, the cube root of a number, and inside we can put a number like 8, and the cube root of 8 is 2, because if you cube 2, 2 times 2 times 2 is 8. We could also do the cube root, let's say, of 27. That turns out to be 3. Because 3 times 3 times 3 is 27. And so these are called radicals. You could have the cube root, you could have the 4th root, the 5th root, the 6th root, the 7th root, and so on. Most of the problems we do, we kind of restrain ourselves to the square root or the cube root. So let's do some problems. So number 1, we want to simplify the square root of 9 divided by 49. The trick to these problems is you have to realize that radicals go through multiplication and division. That means if you have the square root of two things times each other, so let's just say a times b, this will be equal to the square root of a times the square root of b. And it works also for division, so if you take the square root of a divided by b, it will be equal to the square root of a divided by the square root of b. So radicals, we say they go through multiplication, and they also go through division. Now, it's really important to realize that they do not go through addition or subtraction. So if you take the square root of a plus b, it is not equal to the square root of a plus the square root of b. This is something students continuously get wrong, so you want to make sure that this is not true. All right, so we say the radical goes through multiplication, and it goes through division, but it does not go through addition or subtraction. Alright, so let's try some of these problems out. So let's look at this first one. So here you can see you have the radical and you're dividing, so you can take this through. So this is really the square root of 9 divided by the square root of 49. And when you see these, 9 is a perfect square, it's 3 squared, and 49 is a perfect square, it's 7 squared. So its square root here is 3, and on the bottom we have 7. So let's take a look at the next one. And so the next one we have the square root of 45. Now for the square root of 45, it's not so simple because 45 is not a perfect square. So for example, for the square root of 49, we'd basically be done because the square root, because 49 is actually 7 squared. And the square root of whatever squared is just what's inside there, so that's just equal to the number 7. But we can use this idea and this idea that the radical goes through multiplication to simplify this problem. So this is equal to the square root, and the idea is when you see 45, you should think 45 is equal to 9 times 5. And 9 is a perfect square, so we could rewrite this as 9 is 3 squared times 5. And we know the radical goes through multiplication, so this is the same thing as the square root of 3 squared times the square root of 5. And the square root of 3 squared is whatever's inside there because it's squared, so that's equal to a 3. And then you have root 5 on the end. And that's our answer. If you look down at number 3, instead of having a square root, we have a cube root. And so the cube root of 8 is equal to, and if you look at 8, you can see that you can factor 8 as being 2 times 2 times 2, which is really 2 cubed. And so I can rewrite this as the cube root of 2 cubed. And since you're taking the cube root of a cube, it's whatever's right inside there. So you have the number 2. So the cube root of cube is whatever is right inside there. And so this answer is 2. And then you go down to the next problem right here. And then you run into sort of a similar problem you did in number 2. 32 turns out not to be a perfect cube, but you can still factor it. So let's factor it. So the cube root of 32. There are all kinds of ways to factor 32. So I'm going to say this is equal to, I can do like 2 times 16. And then 16 can be factored as 2 times 8. So that's equal to 2 times 2 times 8. Oh, and 8's 2 cubed. All right, so this is actually 2 times 2 times 2 times 2 times 2. And what I can do here then is I can put the cube together. These right here give me cube. And so I'll write this as the cube root of 2 cubed times 2 squared. Oops. That's supposed to be a square. Right, so the cube root of 2 cubed times 2 squared. And if it's cube, you can pull it out. So if it's cube, you can pull out whatever's inside there. So it just gives you a 2. And you have cube root of 2. And so that's my answer. 2 times cube root of 2. Oh, and there was a mistake here. This is actually 2 squared. And there's still the square there. And so that's actually then 2 the cube root of 4. And that's my answer. All right, let's look at the next one. And we want to simplify this thing, the square root of 75 minus 3 root 27. So again, the idea is try to simplify these things individually and see what happens. So can you simplify the square root of 75 and the square root of 27? So when you see 25, and this is square root, so I see 25 times 3. So 75 is really 5 squared times 3 minus, and then I have a 3 here. And then 27, I think 27, my times tables tell me that's 9 times 3. So that's 3 squared times 3. Right, the idea is we want everything in terms of squares because it's a square root. Everything for cube roots you want to write in terms of cubes because then you can pull out whatever you're cubing. Here I can pull out whatever I'm squaring because again, remember the radical goes through multiplication. So if we do this step by step, you'll see that I can say this is the square root of 5 squared times the square root of 3 minus 3 times the square root of 3 squared times the square root of 3. So this is, I'm showing every step here. You could actually skip this step if you really wanted to. Which then this is equal to, so the square root of a square is whatever's inside there, so you get back 5, and then you have root 3, minus, you have 3 times the square root of a square is whatever's inside there, so that's a 3, and you have a root 3 on the end. And so that's equal to 5 square root of 3 minus 9 square root of 3, which is then equal to, I have 5 of these minus 9 of these, and so I'm going to get negative 4 of these. And so my answer is negative 4 root 3. Let's take a look at number 6. So on number 6, instead of subtracting or adding, I'm multiplying on this one. So this is going to be equal to, and so I guess the first thing I would probably do is try to factor some of these things to pull out the squares. And so this is 2, the square root, and that's actually 16 times 2. So that's 4 squared times 2. And then I have times, and then 24. Well, what's 24? So you could say it's, what, 3 times 8 or 4 times 6, because that's better, because 4 is 2 squared times 6. That's 24. And I can pull out the squares. So that's going to be equal to 2 times. And then this is going to be 4 because it's 4 squared. So 2 times 4. And then you're left with a root 2 in there. And then times, you can pull out a 2. And you're left with the root 6 in here. And so then you can multiply the numbers together. So you have 2 times 4 times 2. So 2 times 4 is 8. Times 2 is what? 16. And then you have root 2 times root 6. So those you can bring together again. So root 2 times root 6 is root 12, because 12 is 2 times 6. So remember when I wrote this, you can go forwards or backwards. If you have root A times root B, you can just rewrite that as the square root of A times B. It goes either way because it's an equality. And this can actually go a little bit further because 12 can be factored as 4 times 3. So it's equal to 16. The square root of 4 times 3. And you can take the square root of 4. The square root of 4 is 2. So you get 2 times 16, which is 32. And then you have the root 3 left over there. So that's the answer to number 6. All right, let's take a look at number 7, because number 7 uses something called the distributive property, which we haven't talked much about yet. The idea is we want to multiply this thing minus this thing times this thing minus that thing. And the way you do this is you simply distribute each of these through. So when you distribute something, the idea is you give it to each of them. Like if I distribute a soda to each of the students in class, each student gets a soda. So the idea is you take this thing and you're going to multiply it by this, and you're going to multiply it by that. So that's the first step. So this would be equal to square root of 10 times 2 root 5 is equal to 2. The square root, you can combine these, so 10 times 5 is 50. And then minus, because that's a minus, you have root 10 times minus 3, and so you get minus 3 root 10. And so now that you're done with the square root of 10, you have to move on to the negative 2 here, so the minus 2. So this times this, and this times that. So I'm going to get a negative, or a minus. So I have minus 2 times 2 root 5, so I get minus 4, because 2 times 2 is 4, root 5. And then I have a minus 2 times a minus 3 here, or a negative 2 times negative 3, which gives you a plus 6. So you did the multiplication, and now you just need to simplify, and you can't simplify 6, it's 6. You can't simplify root 5, because you can't write 5 as a perfect square. You can't simplify 10, because you can't write 10. You can't factor in terms of any sort of perfect squares. But 50 you can, because 50 is 25 times 2. So realize that this is equal to 2 times the square root, and 50 is actually 25, which is 5 squared, times 2. And then you copy down the other stuff because it's the same. So 3 root 10 minus 4 root 5 plus 6. And then this is equal to, so you can pull out the 5 because the square root of a square is whatever's inside there. So you pull out the 5 and you get 2 times 5, which is 10. You're left with the root 2 inside, and you just copy down the other stuff because they can't be simplified anymore. So 4 root 5 plus 6. Let's look at number 8. Number 8 talks about something that's called rationalizing the denominator. So it's a really sort of simple idea. Some numbers are rational and some are not. Like if you look at the number square root of 2, it's actually not a rational number, which means it can't be written as a fraction, a nice number, a nice integer a divided by a nice integer b. Or if you like, when you look at it on a calculator, so on the calculator, you can take a look at the square root of 2. So you have second, you hit x squared, get the square root, and then you hit 2. And you see you get this 1.414213562. The idea is you get this decimal expansion, and this expansion doesn't repeat. So it just keeps going on. There's no sort of pattern in some sense to it. And that's what makes it actually an irrational number. So you get 1.414 blah blah blah, 414 blah blah blah, and it doesn't really repeat. When you want to rationalize the denominator, that means you have an irrational number in the bottom. So it turns out root 3 is also irrational. And to make it rational, it's actually very simple. You just multiply top and bottom by the same thing. So I'll multiply top and bottom by square root of 3. And if you take square root of 3 times square root of 3, right, what is that equal to? Well, that's equal to the square root of 3 squared. And then on the bottom, and then on the top, you have the square root of 7 times 3, which we'll just write, and then we can compute it. And so this is equal to the square root of 21 on top. And then remember, the square root of anything squared is what's inside there, and so that's just equal to 3. And so and 3 is a nice rational number, right? 3 you can write as 3 divided by 1. So it's a nice, pretty number. And so that's what we call rationalizing the denominator. We can come down here in number 9 and practice one more time. It's given to us in a slightly different form, but it's really not that big a deal because we know that the radical goes through division. So this is really just root 5 divided by root 3. And so it's basically just like the last problem we did up here. And so you multiply top and bottom by root 3 because you want to rationalize the denominator. So the denominator is the thing on the downstairs. So you multiply top and bottom by root 3, which remember you can do because this is just the number 1. Root 3 divided by root 3 is 1, so you're not changing the expression at all, or the numerical value of it. And so this is equal to the square root. 5 times 3 is 15. And then again, root 3 times root 3 will give you back the number 3. And so that's my answer. Once we're done with numbers, we want to move on to letters or expressions involving variables. And so here's sort of our first little example where you notice we do have the number 4, but we have the variable y. And so how do we work with this? And it's actually pretty simple, and I'm going to do these the long way, and then when you get comfortable with them, you can shorten them quite a bit if you like. So the idea is write everything in terms of squares, or as much as you possibly can in terms of squares. So that's what I'm going to do. So when I look at this, I know 4 is 2 squared, so I'm going to write 2 squared for it. And then y to the 14. So y to the 14, you can break that into lots of different squares. So it's like y squared times y squared. That's y to the 4th, really. You add exponents here. And then times y squared again. That's y to the 6th. Times y squared gives you y to the 8th. Times y squared is y to the 10th. Times y squared is y to the 12th. Times y squared again is y to the 14th. And then what you can do is you can take this radical through multiplication. So I can just take this and say, hey, this is the square root of 2 squared, the square root of y squared, the square root of y squared, the square root of y squared, and keep going, the square root of y squared, the square root of y squared, and the square root of y squared, and I think I need one more, the square root of y squared. I should have 7 of them. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And of course, what is that equal to? Well, the square root of a square is whatever's inside there, so you get 2 for that one, and then y. So 7 of these things. So y times y times y times y times y times y times y, which you can rewrite as 2 times y to the 7th. And so that's the answer for that one. Now, some of you that are rather familiar with these, you can actually do this a lot faster. So you can think of this thing as being equal to, and you really don't need to do the 4 because everybody knows the square root of 4 is 2 if you're really good at these. But y to the 14 can be rewritten as y to the 7th all squared. Because when you write this, exponents don't add, they actually multiply. So if you think about this, what is y to the 7th when you put a 2 in the exponent? Well, that means take y to the 7th times y to the 7th. Oh, so that is just y to the 14 because their exponents will just add. Because you have y times y times y times y times y times y, right? 7 times there. Same thing here, and you get y to the 14. But if you do this, then you can look at this and say, hey, that's the square root of 4, which is 2, times the square root of y to the 7th squared. Oh, so the squares in some sense, the square root takes care of that square, and you just get back y to the 7th. So there are quicker ways to do this, but if you struggle with these a bit, you should just write them out. And after you get really comfortable with this, then you can do it the other way. But I would do it like this for now. Let's take a look at another problem. All right, so here's a problem. You have the square root of 27 times u to the 14th. So it's very similar to the last one. The only real difference is that 27 is not a perfect square. So when I see 27, I know it's 9 times 3, so that's really 3 squared times 3. And then you do the same thing with u to the 14th. It's, u squared, u squared, u squared, u squared. So right now I have u to the 8th because you add those exponents. And then u squared, u squared. So what's that? U to the 12th, and then u squared. So let's extend this radical. And so you should have 7 of these because when you add them up, you get 14. And then, of course, this is equal to then the square root of 3 squared times the square root of 3 times the square root of u squared 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 times the square root of u squared. So that's 1, 2, 3, 4, 5. We need 2 more. Square root of u squared, square root of u squared. And then you get your answer. So this is 3 root 3. Right? The square root of 3 squared is just whatever's inside there. So that's a 3. And these are all u. So u times u times u times u times u times u times u. That's 4, 7. There you are. And so this would be, the answer for this would be then, I'd write this as 3 times, and you can write the u's in front. It doesn't matter where you write the u's because this is multiplication. So you have 7 of them, so u to the 7th, and then square root of 3. So remember, in multiplication, you can move all kinds of things around. Like 2 times 3 is the same as 3 times 2. So it doesn't matter which one comes first or which one comes last when you're working with multiplication. Okay, let's move on to the next one. So here I have the square root of 8 times t to the 5th times u to the 8th. So now we're mixing multiple letters, multiple variables. And so, don't be afraid. You just basically do the same thing. So it's the square root. And 8 is 4 times 2, so that's 2 squared times 2. So again, the whole game is try to write things in terms squared because it's a square root. And then you can pull out whatever's inside there. So then you have t squared. That's 2 of them. Another t squared, that's t to the 4th, and then you're left over with one more t, so t to the 1. So we just write t there. And then times, you can write u to the 8th as u squared times u squared times u squared times u squared. And then you can take this radical all the way through here. If you want to simplify this a little bit, you could just say, hey, I don't need to do this next step. I know that the square root of 2 squared is 2. And then I have a square root of 2 next to it. The square root of t squared is t. The square root of t squared is another t. Then I'm left with just a square root of t. And then the square root of u is u. Square root of u squared is u. Square root of u squared is u. Oh, square root of u squared is u. Square root of u squared is u. And so that's what I'm left with. And I can combine the sort of like terms here. So what do I have? I have 2 root 2 t squared with a root t here and u to the 4th. And you can go one step further. So what I would do is I'd write this 2 here, the t squared next to it, and the u to the 4th next to it, because again, this is multiplication, and you can move these terms all around because it's the fancy word for this, it's commutative. So you can just kind of commute things, switch things out. And so then you're left over with root 2 times root t. And remember, you can combine those because radicals go through multiplication and division. So this is actually 2, the square root of 2, t. Right? Again, it goes both ways. So if you have the root of something times the root of something else, you can combine these things and say, hey, it's root of this times that. Right? So root a times root b is the same as root a b. All right, so this is my final answer right here. Let's do some more. All right, so number 13. Okay, so now instead of a square root, you have to realize we have a cube root. So the game changes just a little bit. Instead of writing things in terms of squares, you want to write things in terms of cubes. And then you can pull out that if it's cubed. So here I have 40. And when I see 40, my times table is telling me that, hey, this is 8 times 5. And 8 is actually 2 cubed. So that's great. So it's 2 cubed times 5. And then t to the 8th, it can be written as t cubed times t cubed. So that's really t to the 6th times t squared. So that's t to the 8th. And then w cubed is already cubed, so you just write it down, w cubed. And if you want to show all the work, you can just say, okay, this is then equal to, oh, and that's a cube root, so we should put a 3 here. So this is equal to the cube root of 2 cubed, which is great because that means that's just going to be equal to 2, times the cube root of 5, so that just stays the cube root of 5, times the cube root of t cubed, which is great because that'll wind up being t, times the cube root of t cubed, which again is great, that'll wind up being t, times the cube root of t squared, there's nothing you can do to that, so it just stays like that, times the cube root of w cubed, which again is great, that'll wind up being w. So this is equal to, and that's the cube root, not 3 times, so cube root of t cubed, which is 2, times the cube root of 5, times the cube root of t cubed, which is t, times another t, times the cube root of t squared, and then times the cube root of w cubed is just, again, w. And so this is equal to, we'll combine these, so we have 2, and move the t's out to the front, so you have t squared, and then w here. And now this cube root and this cube root can be combined, just like we did up here. The fact that there are square roots doesn't matter. You can put cube roots on these. The cube root of a times the cube root of b is the cube root of a times b. And so this is the cube root of 5 times t squared. And we're all done with this one. Let's go down to the next one here, 14. And here we're going to work with some subtraction. and then we'll solve some equations involving radicals. So let's finish off with this subtraction problem. And again, the idea is try to simplify these as much as possible, and maybe they'll turn into like terms. Like terms mean they look the same and you can combine them. So let's start with this. I have 4x. There's nothing I need to do with that. And I have the square root. And I have 27. So the idea again is you want to try to write this in terms of squares. And 27, my brain says, hey, that's 9 times 3. And that really then is 3 squared times 3. And then u cubed can be written as u squared times u. And then I have minus a u and then the square root. 75, my brain says, hey, that's 25 times 3, and 25 is a perfect square, so it's really 5 squared times 3. And then times u and times x squared. There's nothing I can do with those, so I just leave them alone. And so what's that equal to? Well, that's equal to, well, anything that's squared I can pull out. So that's going to be 4x, and then that 3, because it's squared, I can pull out, so times 3. And I can also pull out this u, so u squared, I can pull out a u. And then I have a square root of then 3u left over inside there. Minus, then I have u times, and 5 is squared, so I can pull out a 5. And x is squared, so you can pull out an x. And you're left with, again, another square root of 3u, which is really nice because these are like terms now. Now let me clean it up a bit. So I have 4 times 3, which is 12. And then I have xu and square root of 3u, minus, then I have 5 x times u and square root of 3u. So these are actually like terms in the sense that when you look at them, you have 12 of these. Oh, and this is, I'm not sure why that says equals. That should be minus, right? Then minus, right, minus 5 of these. These are the same thing, xu square root of 3u. So if you take 12 things and you take away 5 of the same things, well, how many things are you left with? I think you're left with 7, right? $12 take away $5 is $7. So you have 7 xu root 3u's. And that's my answer. All right, let's finish this off with solving some equations involving radicals. So here we want to solve this equation, the square root of w minus 6 equal to 6. And the idea is you have to get rid of the square root. So it's not too hard to undo a square root. You just do its opposite. The fancy way to say this is to do its inverse, right? So the inverse of the square root is the square. So the inverse of square root is taking something and squaring it. The inverse of a cube root is taking something and cubing it. It's sort of like the inverse of addition is subtraction. The inverse of multiplication is division. So if you have the square root of w minus 6 equal to 6, and you want to solve for w, the problem is w is under that radical. It's under that square root sign. So how do you undo it? You're just going to square both sides. And that will undo the square root. Right, so the square root squared undoes it, and you get w minus 6 on the left equal to 36 on the right. And then you add 6 to both sides, and you get w equal to 42. And so there's my answer. You should check your work, right? So the original equation was this, the square root of w minus 6 equal to 6. And so if you plug in 42, you get the square root of 42 minus 6. And the question is that equal to 6? And if we did it right, it will be. And so that's the square root. 42 minus 6 is 36. And certainly the square root of 36 is equal to 6. So it checks. That means we did it right. So my answer is right here, the w equal to 42. And then the last problem we want to look at is, I guess it didn't. There it is right there, number 16. We have the square root of 5x plus 10 equal to the square root of 7x minus 12. And so how do you undo a square root? You take the square of it. So we square both sides. It should maintain the equality. All right, so this and this are equal, so if you square this and you square this, you should still remain equal. And that undoes that square root, so you're going to get 5x plus 10 on the left. And then you're going to get 7x minus 12 on the right. The idea is get all the x stuff to one side and all the other stuff to the other. So let's move over the 5x first. We'll do this nice and slow. And so what do we get on the left? You just have 10. And on the right, you have 7x, take away 5x, which gives you 2x, right? 7 of these, take away 5 of these is 2 of these. And then minus 12. And then you add 12 to both sides. And you get your answer of 22 equal to 2x. And now you want to undo the multiplication. So you do its inverse, which is divide. So we'll divide by 2. Divide by 2. And you get 11. Right, 22 over 2. Remember, 22 over 2, that's actually equal to, what, 11 times 2 over 2? So the 2's cancel, and you're left with 11 on the top is equal to x. And you can check your work by plugging into the original equation. So the original equation was 5x plus 10. The square root of that, is that equal to the square root of 7x minus 12? And so when you plug in x on this side, we plug in x equal 11, you get 5 times 11 plus 10. And the question is, hey, is that equal to 7 times 11 minus 12? And if I didn't make any mistakes, algebra mistakes, then it will be. So on the left, you compute this. 5 times 11 is 55, plus 10 is 65. That checks. That's good. And on the right, 7 times 11 is 77. And then you have minus 12. So is that equal? This one was easy because they're in terms of 5s and 10s. But this one I have to think a little bit. So 77 minus 12. Well, I take off 10 and get to 67, and take off 2 more and I get to 65. So they are equal. It does check, so I know I did it right.